So I wanted to take a few minutes and go over the acceleration homework problems. We're going to be using the 5 equations of motion. Question 1, we have a sports car and it goes from 0 to 60 miles per hour in a certain amount of time. And so velocity 1 is 0. Velocity 2 here is 60 miles per hour. We're going to have to convert that to meters. Time 1, of course, is 0, and time 2 is 5.00 seconds. So step 1, you're going to need to convert this. And the conversion factor is 1609. So using conversion factors, you need to decide, do the miles go on the top? Do the miles go on the bottom? Well, look at the units you're trying to end up with. You want to end up with meters on top, because the miles will then cross out and you're left with units of meters in the numerator, which you want. Now you have to deal with the time. We need that in seconds. So you know there's 60 seconds in a minute, 60 minutes in an hour, and 60 times 60 is 3600. Now why did I write it with the hour on top? Because I'm trying to eliminate the hours and end up with seconds down in the denominator. So we need the 3600 to be on the bottom. So this conversion is just 60 times 1609 divided by 3600. I'm getting something like this in units of meters per second for the final velocity. Now you need to ask yourself, how many significant figures can I carry? I can't carry 6 significant figures. Let's see, look at the 60. Basically we have to assume that's 60 with a decimal point. The time is given with 3 significant figures. We're really limited to 2, strictly speaking. I would say just write 27. So the first question is asking for the average acceleration in meters per second squared. The equation you want to use, from the 5 above, it's the second one in the list, which is the same as that. Plug in the values and limiting ourselves to 2 significant figures. That's the answer I get. Check it against the hint. Yes, it lies within 5 and 6. Part B, how far does it travel in meters during this time? So the first thing you want to do is choose the appropriate formula from these 5. This one here has distance and this one has distance. This term's going to drop out because it's 0. So all we need is the average acceleration, which we just calculated, 5.4 meters per squared, and the time, which is 5.00 seconds squared. And just run that out and make sure your answer is somewhere between 60 and 70. The units, of course, would be meters. And don't forget to square the time. Again, draw a diagram. It says the barrel of the gun is 127 millimeters. And it's asking us to report things in meters. So right away, you should convert that into meters. It's pretty easy. There are 1,000 millimeters in a meter. So what's 127 divided by 1,000? You don't need a calculator for that. It's just 0.127 meters. Just move the decimal point back 3 places. And what else do we know? Velocity 1 before the bullet gets fired is 0, of course. Velocity 2, so come up again to the 5 equations of motion. So we can't use 3 and we can't use 4 because we don't know the time involved. So equation 5 is the one we would want to use for this. We know that this number is 0. The initial velocity is 0, so that term drops out. So then ask yourself, how do we isolate A all by itself on one side of the equation? It's just simple algebra. Divide both sides by 2x, like that. This term drops out because that's 0. So we're left with A isolated on one side of the equation and final velocity squared over 2x. You would plug in 127 for x, and you would plug in the final velocity, 335 meters per second, and be sure to square that, and that will give you the acceleration in meters per second squared. It's a big number. You need to fall within this range between 400,000 and 500,000. Part B, how long in seconds is the bullet in the barrel? And for this, you could just simply use equation number 2. Those cancel out, and you're left with time equals change in velocity over acceleration. You just solved that right there, and the change in velocity is, change in velocity is v2 minus v1 divided by the average acceleration, which you just solved for. And so go ahead and solve that, and you should be landing somewhere within that range. And the units, of course, is seconds. Now we're sort of limited to 3 significant figures here because of the 335. Question 3 just turns the problem on its side. It's a free fall, what we call a free fall problem. And so this person is falling for 6 seconds, 6.0 seconds. Their initial velocity is obviously 0. We don't know what their final velocity is after 6 seconds. That's what we're trying to solve for. What is causing them to accelerate? The acceleration due to gravity. The problem is pretty simple. It just uses equation number 2, and then we're trying to solve for v2, in essence. We're trying to solve for that. Now, it's made easier because velocity 1 is 0. So that goes away. So really, in this case, now since we're trying to solve for that, bring the t over on this side. So the average acceleration is 9.8 meters per second squared. The time is given in the problem as 6.0 seconds. And you just multiply those. And we're sort of limited to, we're given the time as 6.0. We're limited to 2 significant figures with this problem, and your answer should lie somewhere between 50 and 60 meters per second. Here's another free fall type of problem. Draw a sketch, very, very important, and just write down whatever information you're given. How do we know the average acceleration is 9.8? Because that is the acceleration due to gravity on planet Earth at sea level and so forth. We know the initial velocity is 0, the final velocity just before impact we don't know, but the problem isn't really asking for that anyway. What the problem wants to know is what is the height of the cliff, knowing that it took 4.5 seconds for this object to reach the bottom. Now we're not really working in the x-axis here, so notice I didn't write delta x. We're actually working in the y-axis, up and down the vertical axis, so you could put delta y. I just prefer to use delta d for distance. v1 is 0, so that whole term zeroes out. What's a? 9.8 meters per second squared. What's t? T is given in the problem. Let's see, this problem was 4.5 seconds. And don't forget to square that. And your answer for the height of the cliff, of course, will be in meters. And you should fall within this range, 50 to 100. And I'll just give you a clue. It's a lot closer to 100 than it is to 50. So when you step back and think about it, what have we done? We've just measured the height of a cliff by dropping a rock off the cliff and measuring the time it took to hit the bottom. And so these equations are pretty powerful and useful. This question just reverses it. Now the ball is being thrown up in the air. It says a child because they want you to think the ball starts right at the ground. A child is small. Otherwise, you would have to subtract the height that the ball started from if it was an adult, basically. So here you have to assume that this is the ground level right across here. So we're given the initial velocity, 4.9. What is the maximum height? So we're trying to solve for delta D. And we know that the acceleration is working against us here, the acceleration of gravity. So the way I have set this up with velocity being positive going upward, I need to set the acceleration negative because it's working against me. Now I could have set the problem up with, velocity 1 being negative 4.9, velocity 2 being 0, and the acceleration being positive, and I would get the same result. But you do need to keep track of your signage and realize that acceleration is working against you with this one, so it needs to have the opposite sign. So looking at the 5 equations, 4 and 5 both have a delta x term in them, but equation 4 requires us to know the time. So looking at the equation, we're trying to solve for x down here. How can we isolate that on one side? Well, we know that v2, v sub 2, the final velocity, that term zeroes out because it's 0 squared. That goes away and we're left with this. This is just a bit of algebra. And at this point, how do we isolate x over here? We divide both sides by this. So this goes away, and you can rewrite it all in terms of distance. So this would be negative 4.9 squared. On the bottom, you're going to have a 2 and a minus 9.8. Like, it's not negative 4.9 quantity squared. It's 4.9 squared. Get a number, and then put a negative sign out in front of it. And you divide it by 2 and divide it by negative 9.8 in the denominators. It's closer to the 1 than it is to the 2. This one is plotting the velocity of a motorcycle cup. So time is down here and velocity is right here. So at time equals 3 seconds, which is right here, come up. That intersects the graph right here. What is his acceleration there? Well, we know his velocity is 20 meters per second, and it's not changing. Between about 0 seconds and 5.5 seconds, it doesn't change. So he's just moving at a constant velocity. So we know the acceleration is going to be 0, but how do we show that? Velocity 2 minus velocity 1. So let's just grab 2 points. How about 4 and 2? So let's make that the final, and we'll make that the initial, and the time span between 2 and 4 is 2 seconds. All right, what is his velocity at 4 seconds? It's 20. What is his velocity at 2 seconds? Also 20. See, I'm looking here, I'm coming up 2, intersecting there, I'm going over here, and it says 20. Okay, so it really doesn't matter what we have in the denominator, it's still going to be 0. Average acceleration, instantaneous acceleration at 3 seconds is 0 meters per second squared. Let's take a look at 7 seconds. 7 seconds is here, come up, it hits the curve about right there. And at that point, his velocity is about 32 meters per second. What's happening to his velocity during this section of the curve? It's going up with time. So he's accelerating. He's going faster. You see, at 5.5 seconds, he was going 20 meters per second. And at about 9 seconds into this, he's going about 43 meters per second. So he's obviously accelerating. So if we grab a portion of the curve, let's say between 9 seconds and 6 seconds, we should be able to get a reading on his acceleration because the graph is a straight line within that section. What do we use for time? Well, the time elapsed between 9 and 6 is 3 seconds. Now plug in the value. What's his velocity at 9? I'm saying about 43 meters per second. How about 6 seconds? I would guess about 23. 3 seconds in the denominator. So that gives us 20 over 3, 6.7, let's say, meters per second squared there would be his acceleration at that point. How about 11 seconds? I'm going to let you do this, but notice the curve is going down. That means he's decelerating. Between about 9 and 13, he's decelerating, actually all the way down to a stop down here at 13 seconds. So we're going to have a negative acceleration, we know that. Just pick a useful part of the curve, let's say between 10 and 12 seconds, and set it up the same way. So the velocity at 10 would be, I don't know, 33 meters per second. The velocity at 12 would be maybe 12. Set it up, keep track of your signage, you get a negative acceleration for that one. And in the denominator, you would have 2 seconds. Here we are plotting the motion of a cat. And so on the y-axis, we have the velocity, this time in centimeters per second. And on the x-axis, we have time. 4 seconds, the cat's velocity is about 2.5, roughly speaking, meters per second. At 7 seconds, maybe minus -1 meters per second. So in other words, at that point, the cat would be, I guess, moving towards you. Up here in this area, the cat would be slowing down but moving away from you. Down here at the tail end, the cat has turned around. See, right at 6 seconds, the velocity is 0. The cat apparently turned around and now is walking back towards you at that point. B is asking about acceleration. And so we would have velocity final minus velocity initial, which would be v6 minus v0 over 6 seconds. That's the amount of time that elapses. So velocity at 6 seconds is 0 centimeters per second. Right here at 6 seconds, it's 0. Minus velocity at 0 seconds is 8 centimeters per second. So we have minus 8 centimeters per second, not meters per second, centimeters per second squared. Gives us that value for the average acceleration. It's negative, so it's a deceleration, it's a slowing down. And that's the acceleration at all 3 of these times, 3 seconds, 6 seconds, and 7 seconds, because it's a straight line. If the line had been like this, that wouldn't be the case. We would have to calculate it at each point. In this problem, the trick is to recognize that 20 light years is not time, it's distance. Go to your favorite search engine and type in light year, and so you're given a value. And so here I've kind of rounded it off. 1 light year is about 9.5 times 10 to the 12th kilometer. And these spores have to travel 20 of those, so you will need to multiply that by 20. The velocity that they're traveling is given here, 1,000 kilometers per second. Extremely fast, in other words, 600 miles per second. All right, and it's asking how many years would it take them to make the journey. And so in the problem, you're given the distance, or you can look up the distance. You're given the velocity, and it's a constant, and it's asking for time in years. And so you're going to need to do a couple of conversions and just carefully key everything in. So if you have any questions about this homework, please let me know.